Okay, so Chapter 1 Introduction Recap. So, artificial intelligence is a field of study where we look to intelligent software to automate routine labor, understand speech or images, make diagnosis in medicine, and support basic scientific research. So the basic version of it is a knowledge-based approach where we tell the AI what the rules are. A computer can reason automatically without statements in these formal languages using logical inference rules. And an advanced form of that is machine learning, where instead of using hard-coded knowledge to guide AI systems, we're providing raw data where AI will be acquiring their own knowledge by extracting patterns in those raw data. And an example of simple machine learning algorithm is called logistic regression. Logistic regression is solving problems involving knowledge of the real world and making decisions that appear subjective. The performance of machine learning algorithms that are simple depends on the representation of the data. So the AI system is provided with several pieces of relevant information that will be used for the solution. So each piece of information included in the representation of the patient is known as a feature. So when there's a patient and there are some medical information that are relevant to the diagnosis, we are not giving the AI the patient itself, but only the important knowledge and information about that specific task. So if we're looking at say this one is giving an example of C-section, it's gonna provide like if there's like scarring in the uterus or the like, or the age of the patient, and so on and so forth. So that is how we are representing the patient, and whether they have scarring is a feature of the representation of the patient. So another example of AI is representation learning. One solution to the problem of raw data being noisy, which means that the raw data is not ideal. So in this book, it's providing an example of photos of cars, and AI is supposed to detect the image of a car from any image that's provided, but it can be obscured by obstacles in front of the cars, like it's hidden halfway behind a tree, or if the sun's so bright that lighting is kind of, ruining the photo, then AI won't be able to infer that that is a photo of a car. So one solution to that problem is to use machine learning to discover not only the mapping from the representation to the output, but also the representation itself. So it sounds ridiculous, but what it actually means is that instead of telling the AI, hey, if there's a photo of a solid object with edges enclosing them with two wheels, and it's gonna tell the AI what wheels look like, so they can determine whether they're wheels, and they're supposed to be on the ground, not necessarily but usually, and there are 4 sets of wheels, but you might only be able to see 2, and they're parallel, and so forth. These rules are provided, but as I just discussed, there might be issues with the photo images quality. So a solution to this noise problem is representation learning. So learned representations often result in much better performance than can be obtained with hand-designed representations. So it is to make machine learning learn about the representation. So instead of telling the AI what are the important features of a patient if you want to provide a diagnosis for C-section, we will just continuously give it raw data so that AI is able to learn what car should represent, or what C-section diagnosis patient whom we should diagnose C-section looks like. So its advantage is obviously how AI can adapt to new tasks, because it has learned the trade instead of it's not given the fish, it's given a guide as to how to fish. Well, that was a bad description. So instead of giving AI fish itself, we're teaching them how it should be fishing to get fish in the end. Sorta. That was a bad analogy, but you know what I mean. Hopefully. So representation learning algorithm is used in autoencoders. So for audios, there are various formats in which it can be in. It can be in MP3 format, MP4 format, or like these fancy new formats that we have for better, higher quality audio files. So it encodes and decodes it, and representation learning enables the autoencoder to know how to encode and decode to keep the quality and certain features that we care about, and but also be fast, because we care about how long it takes to encode or decode. So it's figuring out the best way to do that. So when designing features or algorithms for learning features, our goal is usually to separate the factors of variation that explain the observed data. We want to separate the factors of variation. So we want to know what in the formula is changing and what in the formula is distinguishing it from the different parts. So factors is separate sources of influence. Factors are usually not combined by multiplication. Factors are often not quantities that are directly observed, but they are unobserved objects or unobserved forces in the physical world that affect observable quantities. So it's not like how many numbers of cookies are in the photo, but something that we can sort of infer. So here, when analyzing an image of a car, the factors of variation include the position of the car, its color, and the angle and brightness of the sun, as we talked about. So we want to disentangle the factors of variation and discard the ones that we do not care about for a better solution. So, but it can be very difficult to do at a high level. Abstract features. Extracting them from raw data can be very difficult. The factors of variation are very, very difficult to identify, even for humans in some cases. So deep learning is a solution to that problem. So deep learning solves the central problem in representation learning by introducing representations that are expressed in terms of other simpler representations. So it's kind of like divide and conquer. Instead of looking at this big, huge problem of detecting a car, it can be come up with how to detect tires. And then if you go even smaller, how to detect a circle. Like, what is a circle? So figure 1.2 shows how a deep learning system can represent the concept of an image of a person by combining simpler concepts such as corners and contours, which are in turn defined in terms of edges. Which makes sense, huh? So we are finally getting to the definition of MLP. MLP stands for multi-layer perceptron. Multi-layer perceptron. So this MLP, multi-layer perceptron, is an example of a deep learning model. It is a mathematical function mapping one set of input values to output values. So if you put X in, you get Y out. Very simple. At least in the concept, in this way. The function is formed by composing much simpler functions. We can think of each application of a different mathematical function as providing a new representation of the input, so different angles, in other words. The idea of learning the right representation for the data provides one perspective on deep learning. Another perspective of deep learning is that depth enables the computer to learn a multi-step computer program. Each layer of the representation can be thought of as the state of the computer's memory after executing another set of instructions in parallel. Well, let's go to 1.2. So this is the output. We are giving AI an image, and we want to know whether it's a picture of a car, a person, or animal. So if you look at the picture, it's obviously a person. But how do we make computer know that this is a photo of a person, although it's really in bad quality? So it can identify visible layer, so pixels. Computer obviously knows that the color of this specific pixel, this pixel, this pixel, and so on. So if it's finding combination of these pixels as these, then you can see edges, because it seems that it's divided here between green and purple, and there are lines here between blue and, what do I call this, peach-ish, and likely here. So from these edges we can get to corners. You see how this is kind of like a corner, and contours, these circular-ish shapes. And then from this we can finally find hidden layer, the third of that, where we can identify objects. Cars have wheels like these, person has a face like this, animal, I don't really know what this is, but bam, it's not a car or a person, so that must be animal. So we can identify the object. So this task of identifying an object is broken down into identifying smaller parts that compose the bigger solution. So this is probably how they explain it in much better, concise words. So I'll read it. Figure 1.2, illustration of a deep learning model. It is difficult for a computer to understand the meaning of raw sensory input data, such as this image represented as a collection of pixel values. The function mapping from a set of pixels to an object identity is very complicated. Learning or evaluating this mapping seems insurmountable if tackled directly. Deep learning solves this difficulty by breaking the desired complicated mapping into a series of nested simple mappings, each described by a different layer of the model. The input is presented at the visible layer, so named because it contains the variables that we are able to observe. Then a series of hidden layers extracts increasingly abstract features from the image. These layers are called hidden because their values are not given in the data. Instead, the model must determine which concepts are useful for explaining the relationships in the observed data. The images here are visualizations of the kind of feature represented by each hidden unit. Given the pixels, the first layer can easily identify edges by comparing the brightness of neighboring pixels. Given the first hidden layer's description of the edges, the second hidden layer can easily search for corners and extended contours, which are recognizable as collections of edges. Given the second hidden layer's description in the image in terms of corners and contours, the third hidden layer can detect entire parts of specific objects by finding scientific. I will repeat that sentence. Given the second hidden layer's description of the image in terms of corners and contours, the third hidden layer can detect entire parts of specific objects by finding specific collections of contours and corners. Finally, this description of an image in terms of the object parts it contains can be used to recognize the objects present in the image. Images reproduced with permission from these guys. I don't know how to pronounce their names, but I don't feel guilty because they probably don't know how to pronounce my name. So yeah, going back to the last paragraph. So the idea of learning the right representation for the data provides one perspective on deep learning. Another perspective on deep learning is that depth enables the computer to learn a multi-step computer program. Each layer of the representation can be thought of as the state of computer's memory after executing another set of instructions in parallel. Networks with greater depth can execute more instructions in sequence. Sequential instructions offer great power because later instructions can refer back to the results of earlier instructions. According to this view of deep learning, not all the information in the layers activations necessarily encodes factors of variation that explain the input. The representation also stores state information that helps to execute a program that can make sense of the input. This state information could be analogous to a counter or pointer in a traditional computer program. It has nothing to do with the contents of the input specifically, but it helps the model to organize its processing. Okay. So, to explain this, sequential instructions are powerful because later instructions can look at the previous instructions results and use that. In this view of deep learning, not all the information in the layer's activations necessarily encodes factors of variation that explain the input. So, not all the information from the layer is necessarily useful in explaining the input. No, explaining the factors of variation, that which explains the input. So not all the information on a layer is useful for finding the factors of variation. The representation also stores state information that helps to execute a program that can make sense of the input, which is kind of like counter or pointer, which has nothing to do with the inputs related to its content, but it helps the model to organize its processing. Makes sense. So there are two main ways of measuring the depth of a model. The first view is based on the number of sequential instructions that must be executed to evaluate the architecture. Two ways of measuring the depth of a model. First, number of sequential instructions that must be executed to evaluate the architecture. We can think of this as the length of the longest path through a flowchart that describes how to compute each of the model's outputs given its inputs. Just as two equivalent computer programs will have different lengths depending on which language the program is written in, the same function may be drawn as a flowchart with different depths depending on which functions we allow to be used as individual steps in the flowchart. So figure 1.3 illustrates how this choice of language can give two different measurements for the same architecture. So figure, I need to be, oh, that just got very small. Oh no, I'm telling the world that I use Telegram, Chrome, Firefox, and these other apps. I'm gonna make this, yep, there you go. Okay, so figure 1.3, illustration of computational graphs mapping an input to an output where each node performs an operation. Okay, I think my laundry is done, so I'm gonna stop here and continue.